Good afternoon, everybody. Thanks for coming to this talk. So today we are going to hear from Lak on the topic of MLOps. So very interestingly, I know Lak through Twitter. So I follow him on Twitter. He follows me on Twitter. And yesterday evening, he messaged, sent me a DM saying that he's in Bangalore. And I was like, this is the best opportunity for us to listen to him directly on the emerging buzzword, MLOps, and take it forward. Over to you.
Yeah, thanks, Deepak. So this talk came together on really short notice. But this is a topic I've been thinking about for a while. So just having Deepak's invitation to come talk at IAC gave me the impetus to finally put down my thoughts on, do you really need MLOps? Right? And my answer here is going to be that it is mostly just a sales pitch, and that you really don't need MLOps. Many of the concepts, they're pretty valid, but there are much simpler ways to get to the solution that's needed. You don't need the unnecessary complexity that that is sold under the buzzword MLOps. Right? But no, we've got to start somewhere, right? So, what is MLOps? What is MLOps? Anybody? It's a concatenation of two things, right? Ops is operations, of course, and this basically comes from this old thing called DevOps, where DevOps was the fact that you had developers and you had people who maintain and manage systems, operations people, right? So when you have systems, you can't just develop a system and just hope that it works. You need to have another team of people. They are monitoring the system to make sure that it is alive, that it basically is serving all of the customers, that it isn't down, that it doesn't have bugs and so on. And it used to be that you would have system administrators, IT people, who would basically manage these systems. And what happened was that people found that it was much better if the operations people could make small changes to the systems themselves. So that was the whole idea behind DevOps, was that you had operations people who weren't basically just treating these systems as black boxes, but they had the ability to make the kind of changes that they wanted to make to the systems that they were managing and maintaining. So what is MLOps? MLOps is essentially DevOps for machine learning systems. Right? So you're really talking about, okay, how can an operations people, how can they administer ML models? Right? So now think about it. You have an operations person who knows how to manage and maintain web systems. They know how to manage and maintain databases. They know how to manage and maintain web services and network relays and switches. Do you want to really have them go maintain your image segmentation model? What is the likelihood that they understand enough of the internals of a machine learning model in order to be able to maintain it? So the idea behind MLOps is, how do we basically get to the point where an operations person can administer a machine learning model? And this all came about, right? So from this perspective of like, there was a very famous paper, Hidden Technical Debt in Machine Learning Systems by Sculley and a bunch of other folks at Google. And the main point about this paper was that it's relatively fast to develop and deploy a machine learning system. Right? You can write an ML model relatively quickly. You can deploy it, but then maintaining it over time becomes really difficult and becomes very expensive, because you don't want to have, yes.
Are people who generate data for the ML models, are they counted under MLOps?
Are people who generate data for ML models? We typically think about people who generate data for ML models as, could be labelers, right? So you really we don't think of them as operations people. If you think of them as, typically you think of them as scorers or labelers, and they tend to be a different team. So the idea here is that developing and deploying is pretty fast, but If you want to maintain an ML model over time, that becomes kind of expensive because you don't want to take your expensive developers and have them go basically give them a pager and have them basically fix things 24/7. And if you give it to an operations person, they don't understand the internals of an ML model. So they don't understand things like data drift. They don't understand things like concept drift. They don't understand how to basically, they make a change. They don't understand where to make the change. And they don't understand how to redeploy the model because the model itself involves a whole bunch of different things, such as data pre-processing and a variety of different things around. So it's not just the machine learning model itself, it's how that data from the book gets sent into the model, all the things that have to happen to the data. And so there's a really viral image that's in that paper. So whenever anyone talks about MLOps, you will see this image out there. So the ML thing that you're talking about is a really, really, really tiny thing. And all around it is all the other things that are important in order to put an ML model into production. So if there's something wrong, somebody has to understand the entire system in order to basically put it, and all that dependency tracking and keeping everything up and alive is something that is kind of hard to block. So that's why MLOps became a thing. Right? How do we get operations people to basically maintain ML models when we're building ML models in this incredibly complex and ad hoc? Answer: don't do things in an ad hoc, right? Make things much more systematic. But the thing to realize is that this paper and this viral image are from 2015. Okay, so that Sculley paper that came out was in 2015, and it is absolutely accurate, even from my perspective, because this is exactly what I was doing in the 2010s. In the 2010s, I was working at NOAA, and I was building machine learning models for weather prediction. Okay? So this is one of the models that we were doing. And if you have a radar, a ground-based radar basically scans the atmosphere. It basically finds anything that's flying. Okay, so anytime, and part of anything that reflects the radar signal. So you get raindrops, but you also get insects. You also get birds. You get a variety of different artifacts that are not rain. You also get a beam that can get refracted back to the ground. So you get what's called ground cloud. So you get a variety of other signals in the data, which if you then take it and put it into a numerical weather forecast model, will basically start creating rain systems where it's actually just keys. So you want to basically clean up the data. And the way that we cleaned up the data was using neural networks. Okay, even back in 2010, we had neural networks. Okay, but the idea was that the way that we created these models was very, 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 like, it was exactly what the Sculley paper was talking about. There's a whole bunch of steps that are needed before we get to the ML model. So even this particular ML model, we had radar data. The radar is basically ground-based data. So it's sitting on the ground, it's scanning. So it's like an ice cream cone. And then it's basically tilting up and scanning again. It's like ice cream cones inside ice cream cones inside ice cream cones. Okay. So we need to take all of that data and we need to basically do some pre-processing, pick up the easy pixels and say, okay, this is rain, this is not rain. But the hard pixels is what we send to the ML model. Because in those days, training an ML model on millions of data points was impossible. Right? So you basically wanted to make your data set small enough that we could actually train things on. Of course, now we train on multiple gigabytes of data, but back then we wanted to basically make our data set on the order of maybe a few megabytes. It's not much larger. So we would basically do some rules to classify the easy stuff, get to the harder things, and then do alignment. So ice cream cones, the ice cream cones, you have to do geographic alignment. So basically build a 3D volume, and within the 3D volume compute 2D and 3D features. Right? So we did feature engineering, and then basically train the machine learning model to classify those pixels as rain or not rain, the probability. But then each of those pixels by themselves, there is a spatial correlation about those pixels. So you carry out morphological operations on those things. So you do the post-processing, and that's what results in image segmentation model. And now that's our system that we've trained. We're going to go run it in real time. What do we need to do? I have to do the exact same set of pre-processing steps before I can do the ML model and do the exact set of post-processing steps. That's good. The machine learning model itself was a neural network. That's great, but I didn't have TensorFlow then. There's something called the Stuttgart Neural Network System, SNNS. Okay, so train the model on SNNS, which had its own batch weird systems, and then recode the equations of the neural network in C++, because that was what was used in real time, and make sure that things like a sigmoid, right, are using the same IEEE floating point arithmetic things, because otherwise the saturation in those areas would be different. So taking care of all of that. And of course, I trained on batch data. I have to basically do things in real time. The data isn't all there at one time. I need to collect the data, make sure that I'm collecting the data the same way that was done in the batch system. And also problems like in real time, you have instrument errors. In the archive data, they've cleaned all of that. So when I trained my model, I had no instrument errors, but in real time, there's instrument errors. How do we do it? So this is the stuff that Sculley is talking about. Okay, so this is the stuff that Sculley is talking about in 2015, that there is incredible technical debt associated with doing any kind of machine learning. But we are not in 2015 anymore. Okay, so now when you talk about like what do we do with MLOps, right? We are really thinking about how do we build a set of standardized processes, technology capabilities, so that we can build, deploy, and operationalize machine learning systems rapidly and reliably. Right? So this is basically the aspiration. That part is absolutely solid. We do need this kind of reliable way to deploy an application such that whatever you did in training is being repeated when you do something. Right? You cannot have that divergence, because if you have the divergence, you don't even know, but your machine learning model is just now wrong, completely wrong. So that's the aspiration. Okay. And the aspiration itself seems good, right? It's fine. What's the problem? The problem is that at a very high level, the way you solve this is through automation. So the idea here is that with MLOps, the whole idea is you want to formalize and automate every step of the machine learning workflow, whether it is feature engineering, whether it's data pre-processing, whether it's a model operations themselves, whether it's a post-processing, whether it's the deployment, whether it is the handling of the survey, every one of these steps, data validation, all of these steps need to be done automated, right? So it's all about automation, because if you do automation, then you don't have to worry about things being ad hoc and somebody fat fingering something in the training system that is done differently in the serving system, right? So this is all of the steps: data validation, preparation, model training, evaluation, validation. Every one of these things needs to be standardized and automated, right? So that is the vision. And if you can do that, that basically gets you a set of capabilities that are in this aspirational goal standardized, right? Standardized for building, deploying, and operationalizing analysis. It gets you that. Does it make sense? So that's the basic idea behind MLOps. But whenever you say automation, right? Why are you doing that automation? You've got to like step back and say, why am I automating things? You're automating things so that ops people can administer ML models, right? You're not automating things for the sake of automation. Automation by itself is not the goal. The goal is operations people administering machine learning models. Sometimes the automation is way too much. It is unnecessary. Okay. What do I mean? Okay. I always like, there's this very famous XKCD cartoon, right? You say, okay, here is this thing, I'm doing it like 3 times. I'm not going to do it 3 times. I'm going to automate it. Okay, so your idea is, I'm going to work in the additional code. I'm going to like basically spend a little bit of time automating it so I don't repeat it again. And then automation takes over and you get a lot of free time. In reality, what happens? That code that you write is going to be wrong. You're going to go debug it. You're going to rethink the way you're going to do it. You're going to do some more. You're going to basically now start maintaining this automated system when your original work that you were doing, right, it's gone. Because you have now the automation has taken a life of its own. You're now basically, all you're doing is automation. You're not doing machine learning anymore. And that is the danger. The danger here is that you're now spending all of your time basically creating these robust bulletproof systems that you forget that you're just solving problems. And the real problem that you need to solve, the only problem you need to solve is get your ML system to a place where an operations team can take it over. It doesn't have to be completely automated. It doesn't have to run, right? It doesn't have to be like you and I are basically get hit by a truck and this thing is still running in the year 2050. That is not the need of automation. The only thing is automation is one way in which an ops person can take over an ML model. But it is not the only thing, right? If there's a simpler way that you can do it such that the ops person can take over an ML model, you should do that instead. Okay. So with that lens, the lens that you don't want to get automation be the end goal, right? You really want to basically get to something that is simple enough that an ops person can maintain it. Take a look at the MLOps architecture on AWS. This is supposed to be like, whenever you basically get a change in an S3 bucket, a new piece of data comes in, or a new piece of code gets submitted, there is this whole spaghetti of serverless functions that spins up and does a whole bunch of things on data validation, on data processing, and everything in order to basically retrain the model. How easy is it going to be to basically maintain and manage and even remember this kind of thing? And I mean, I don't want to pick on AWS. This is Google Cloud. Okay. So this is basically saying, okay, we have like different kinds of people. We have data scientists, we have machine learning engineers, we have different roles. And all of these people are basically going to interact with YAML files that everybody has their own view of the system. It's just complex. It's just complex. Right? It's just that incredible amount of complexity to get to 100% automation is basically what MLOps is getting to be. And that is where the problem comes. This is Databricks, right? We have this ML flow system. We basically will have a training pipeline, a model evaluation pipeline, a consumer pipeline, all of which will run in Spark, will basically run on a data lake. And you have to basically write code in this specific form such that the ML flow system will basically take care of all of the accounting and keeping between it. But then that basically puts all of these really rigid constraints on everything that you do, right? If you want to do your pre-processing in something that's not supported in Spark, forget about it. Okay? And so if you're basically it's going to be okay if you're basically doing ad serving because everybody does ad serving. But if you're solving a problem that's a little bit unique, where we don't basically have ready-built libraries, like all of these systems are going to basically cause you tremendous amount of grief and pain because there is no real support for anything. Right? You will have to end up building all of the containers and everything to do the automation yourself. Okay. So again, I'm not picking on any particular provider. Everybody does the same thing, right? Everybody is like automation for automation's sake. And you basically want to avoid that whole automation for automation's sake MLOps. Okay, and come back to this first principle. The idea behind MLOps is that ops people need to administer ML models, and they can do it without full automation. What do you mean? You don't need to automate something that is now already automatic. If something can be done in a way that it is transparent, it just happens. This is the right way to do it. There's no need to basically build an automation wrapper on top of it. It just happens. And I'll show you an example of that. Okay. A manual step is okay if it is rare enough. Okay. And so remember, if the ops person can't do it, what are they going to do? They're going to escalate to the machine learning development team. And as long as this doesn't happen 10 times a day, as long as it's happening once every 2 weeks, it's fine. It's fine. Manual steps are fine. Okay, you don't need 100% automation. And you can teach ops people new tricks, right? It's not like they're basically stuck in whatever thing that they know. It is possible that you can say, okay, fellows, like learn this thing here, right? Look at this graph and make sure that this graph, like these numbers stay above this threshold. If it seems to be dropping too much, give us a call. That's fine. That's fine. Again, you don't have to basically have this view of people that they have very limited set of skills. There are skills that they can pick up as well. So with that in mind, okay, let's think about like where, like again, come back to the Sculley paper. This is all about technical debt getting built up because things change and your machine learning model that you built is unchanged. So how do you fix it? Right? What are some of the challenges that happen? Well, for example, you have something called training service. That's one that we just talked about. You basically built the system with a bunch of different steps. That's what you're doing in training. And then in your training, in your serving stack, something turns out to be slightly different. And so now there is a difference. Your code doesn't work. Okay, there's a skew. Maybe you have clients who are interested in a capability that has multiple steps in it. Only one of those steps is an ML model. There's a whole bunch of other things. And that entire workflow is what they care about. And that workflow changes. Right? And therefore, your ML model is no longer fit for purpose. Maybe the incoming data to your ML model, the characteristics of that data change over time. Right? There is a data list. Right? The statistics of that data. Maybe this data used to have a mean of 3, now it has a mean of 3.3. Right? Maybe the data had a variance of 4, now it has a variance of 2.7, become much sharper. And therefore, your ML model is no longer as good as it could have been. Maybe the correct answer changes over time. Because it turns out that you really wanted, right, the amount of time that it used to take you to travel from point A to point B used to be 30 minutes, but a new bridge has gotten built. And therefore, the correct answer is no longer 30 minutes. It's actually like 14 minutes. And we need to retrain the model with this new journey time, right? So the correct answer may be different. Maybe you have model fairness issues. So it turns out that your model is basically serving some set of users and some set of geographies better than other sets of users and other sets of geographies. Maybe, right, you basically had your model, right, and somebody checked in new code, and the model basically, you recompile the model, you run the model, but the code hasn't actually, not everything has been changed. So you end up having a partial system. Okay? Maybe you basically, you served out a loan. You said, okay, this person, we're going to reject them for a loan. And that was like 8 months ago. They basically sued you in court. The court case comes along and the judge says, show me the system that you used to basically make the decision. And you're like, that was 8 months ago. We can't replicate it anymore. You can't have that. You need to be able to go back and troubleshoot the old results. Right? So these are all of the reasons, right, why you basically have technical debt come up. So those are some of the key reasons. All of these are still valid. You still need to solve them. Okay. But here's what the full automation solution is. The full automation solution for a training service queue is, here's a tool, we'll call this a feature store. You've got to go buy a feature store and have it in every one of your systems. You want to basically have anything that involves multiple steps, containerize every step, put up an ML pipeline, and have an ML pipeline running on Kubeflow pipelines. Please buy our Kubeflow pipelines. Okay? You want, if your incoming data changes characteristics, what you need to do, you need to basically take a sample of your data, store it, and you need to basically monitor and evaluate that data over time. You have to do continuous evaluation. Okay? The correct answer changes over time, right? Whenever the continuous evaluation drops below a certain threshold, you need to immediately automatically trigger a new thing. So you need to do continuous training all the time. Okay. Model fairness issues arise, something mumbo jumbo MLOps is going to work. Okay. No one quite knows what the answer there is, but the answer is MLOps. parts of the system aren't changed when the new code is being written. What you need a CI/CD system, continuous integration, continuous deployment. Every time a new piece of code hits GitHub, the entire ML pipeline basically gets recompiled, rerun, retrained, and a new model goes out. Okay. You need to be able to troubleshoot old results. Well, here's an ML registry that we can sell you. Here is a data registry we can sell you. Deploy this. That's the automation solution. Does the automation solution work? Absolutely. These are too complex for the vast majority of use cases. Yeah. Think about this whole code business. What fraction of code check-ins end up changing the data that's fed to the ML model sufficiently that the ML model is no longer fit for purpose? And yet, we are saying that you should retrain your ML model each time. Imagine how expensive that becomes. Right? So you've got to be careful here about basically going with going with this whole let's go retrain everything all the time kind of systems, which is what full automation is going to get you. So there is a simpler way for all of these things. Okay, there is a keep it simple solution. Okay, what does that mean? Okay, for example, remember what I talked about my whole workflow here about basically getting the data, aligning it, doing all of that. That was 2015. Things have evolved since then, right? We now have much better machine learning frameworks, much better data frameworks. So for example, I want to get radar data. Today, radar data from NOAA is streamed to S3 and GCS in real time. I would never basically go extract data out of the data. Okay, I would just read it directly off the cloud storage system. So that's there. I would not basically go do all this feature engineering and feature processing because it's unnecessary. I would just use UNet, right? I would use an image segmentation model, which basically has the feature extractors built in. Right? I don't need to actually go devise my own feature engineering systems. And then I would basically take that image segmentation model, export it, and deploy it to a SageMaker or Vertex AI. I get an API. And that API can then get consumed out of something like Apache Beam, which would basically go ahead and create a data pipeline for me, right? And run this in real time. Super easy. All these frameworks exist. They're all serverless. Okay? I can get things done. All of this complexity is gone. There's one bit of thing though. I didn't address these things, right? What about the idea of batch versus real time? Well, the good news is Apache Beam, BEAM, batch and stream. So it basically handles a batch and stream business. But how about instrument errors, training with different effects of post-processing, etc.? Right? Even those are pretty straightforward these days. So as long as I write my pre-processing code in Python, I have to do it in Python. I will do it in the same machine learning framework. Right? I'm doing TensorFlow or Keras. I'll do this in Python. And when I export my Keras model, that pre-processing code, I will just save it as a Lambda layer in my Keras model. So when my Keras model gets exported, it already has all the pre-processing code built in. This is what I meant by if it is automatic, you don't need automation. Okay? All of this is a lot easier now. So essentially all we are saying is train a Keras model, train a Keras UNet model, and deploy it. You don't need anything else. Okay. So yes, in 2015, all these things were difficult, but ever since then, ML frameworks and data frameworks have evolved to address these issues. You don't need any more complexity because the simple solutions are pretty good these days. So you can get away with basically doing the simple things, and that simple solution, right, is essentially what is called the transform path. Make sure that the pre-processing code is part of the model when you export it. And it's like 3 lines in Keras. You take your input, you put your pre-processing layer, and this is the rest of your model, and you basically make your model inputs and outputs. If you export this model, you're done. So it's a super easy thing to do. Okay, and of course, like this is out of the machine learning design patterns book. Right? So there's a bunch of different best practices there. This is one of them. It's a really easy, simple answer to this whole, what used to be incredibly complex with training service queue is super easy these days. So this is all you need to do. Yes.
So it's more of a philosophical discussion on the question, right?
Right.
When you go back to the previous lecture,
Right.
right? This is something more of like writing your own software in-house package.
Right.
Instead, go and buy a GUI and run the code.
Right.
But for the students in academic institutions, you worked on this code, you know what is going behind these black box.
Right.
Unless otherwise someone undergo these steps,
Mm-hmm.
where is the learning curve? How will they know what is going inside this package?
Okay. You're right. It's a bit of a philosophical question, right? If you don't do all of these underlying steps, are you actually learning anything? I mean, this is basically what always technology comes down to, right?
No, if it is only an application point of view, it is again like the engineer solving a problem or a mathematician solving a problem.
Correct.
Both are different.
Right.
So one is the learning curve. The end goal is different.
Yeah.
The end goal is only the application. But I agree that you choose the simplest part.
Absolutely.
But the end goal is like learning and want to understand development technology, then I would still prefer this route.
Right. And as long, but yeah, you're right. It depends on the objective. And I would argue the objective is accuracy, right? And these days with large amounts of data, you're better off letting the ML model learn the pre-processing that's needed, do the feature extraction itself.
And I also agree, but in addition to that, for example, if everyone started to follow that,
Right.
then it's going to develop the package.
No, this is not a package. It's
Okay.
basically just an ML. This is the ML architecture, right? So essentially, the idea is that you now have ML architectures that do a lot of feature processing and feature engineering themselves, and they learn from the data. And we want to use that approach rather than having to do it yourself. So again, you're right. It's a bit of a philosophy as well, but that's what I mean. There's a difference between 2015 and 2022. Okay? ML theory and ML practice have evolved. Yes. Yes.
What you're saying, you're not quite saying that MLOps as concept is just not happy with the way solutions are pitched for. And this is true for pretty much any abstraction that you want. Today I can sit and argue, hey, I can have better code than Spark. I'll just spend maybe 6 months doing that, but it'll be way faster on Spark. So it's the same with any time you have a complex system, you want to build abstractions by the complex.
Yeah.
When you talk about writing YAML files, that's complex. Arguably, writing sort of 1,000 lines of Python code for these complex things. Why do you know complex things?
Except that these are not 1,000 lines of complex code, and these are built-in capabilities of something like Keras. Whereas the YAML files basically add one more layer on top, right? In order to basically provide automation support that then leads to its own set of maintainability headaches, because you now have 3 more levels of interaction. Right? So we are not really talking about additional capability being provided by the frameworks. You're really talking about like automation for automation's sake, rather than something that's providing the simpler capability that you actually.
No, that's not automation. You should say automation because you want automation. You need automation. Not wonder. You need automation. So which is different from saying you need automation. And even over here, for example, the whole CSC pipeline. If it was not a good CSC pipeline, wouldn't be retraining the entire model.
But then okay, so let's talk about a good CI/CD pipeline, right, will not retrain the entire model. So what makes it a good CI/CD pipeline? You have to basically figure out which kinds of changes result in things that need retraining, and you have to basically build in that kind of smarts into your CI/CD pipeline.
That's part of the MLOps pipeline. Part of the MLOps pipeline.
No, because the MLOps tool provider doesn't really know what kind of changes will actually result in significant enough changes in your data. So they will expect you to tell them. And this is what I mean by you start basically adding a lot more mental cognitive overhead to your something that's relatively simple, right? If where we are basically, I'll talk about what my solution there would be. The keep it simple solution would be it doesn't, for in many cases, you may not need it. Okay. So the second problem, right? Someone is interested in a table that involves multiple steps. Only one of it is an ML model. What do? What everybody else in software does. You have a bunch of different independent steps. What do? You make every step a microservice. Make your ML model a microservice. Don't really think about basically making an ML pipeline abstraction. You don't need it. Let each step basically be itself. Your ML model by itself can be a microservice. So the idea being, take your model, wrap it up, so make it itself its own standalone thing, and you're done, right? So that's called a stateless serving function. The incoming data changes characteristics. You can do continuous evaluation, sample the data like whenever it changes. But in reality, right, you discover that your data has changed. What are you going to do? You're going to basically have to have somebody go evaluate that change, figure out if it's necessary or not necessary. There is a human in this field. And therefore, the human is going to say, I probably agree. They've said, let's wait for 2 more weeks. Let's make sure that this change is actually real. And then after 2 weeks, if the change is really real, they say, okay, let's retrain it. What if, right? You just do scheduled retraining. Every 3 months, I'm going to retrain your model. You don't need to basically do all this continuous evaluation stuff. If you basically say that I'm going to retrain your model on a schedule, once a month, once every 3 months, I'm just going to go retrain. A lot simpler because you don't have to build the sampling of the data. You don't have to build the sampling of the ML models. You don't need to basically build your drift detection. All of that is often unnecessary complexity. You can get away with it with just a plain, clean. I'll just do it once in a while, right? I'll just do it once. I'll always do it every month, right? On the 3rd of every month, I'm going to retrain my model. The worst that your model is going to be out of date for 30 days, which is fine. It's an acceptable cost for a lot of unnecessary complexity that's gone on. Same thing with continuous training, right? You basically say, right, instead of training all the time, I will trigger the training if something significant has changed, right? If the evaluation has dropped, but even better, just a scheduled training. Model fairness issues arise, you are going to need a manual check. Okay, that's not something you can automate. It's fine. Have a person do that. Parts of the system are changed when the new code is checked in. Don't do CI/CDs. Simply do a from scratch build. Now, because again, you're now nice because you know that you're going to retrain the model once a month. You want to do a new release of your system once a month, and that once a month, do a from scratch build. And you don't need to basically go figure out what has changed, whether this change is going to affect the system, not affect the system, etc. Just do it on a schedule. Do a release schedule. The things don't need to be continuous. Things can be once a month, and that's fine.
And that is possible because the other parts of the pipeline have become simpler.
Yeah, because the other parts of the pipeline have become simpler.
Otherwise, it's not possible. Then if it's too complex to, for me to bring the data again and then train it once again, and it takes forever to train.
Right.
Then I cannot do that. Right?
Yeah, but then you're absolutely right. If everything else is not streamlined and simple, you will not be able to retrain once a month. You're absolutely. We cannot go back to the bad old office. It still needs to be simple and streamlined. But my point is, there's a point to which that streamlining is helpful, and there's a point beyond which trying to be too smart basically adds a bunch of complexity that we don't really need. So you want to be able to troubleshoot new results. Well, you just need a version control everything. And you just basically have the version controls, and there's now version controls of data, version controls of code. You version control that and you put them. Yeah, the idea behind the stateless serving function is if your capability has multiple steps, make sure that each step is a microservice all by itself.
But isn't that part of the transform pattern?
The transform pattern is the idea that we have a pre-processing code and it is not a microservice. It is saved along with the model. Okay? So in this case, it's not a microservice because the transform is a library. It's a function that's called in response to every request that comes in. So yes, these are actually two Yeah, yes, you're thinking about when should it be a microservice versus when should it be a library. Right, training service queues should be a library, and like multiple independent steps needs to be a serving function. So yeah, yeah, go ahead.
The previous slide.
Yes.
So I don't see much difference between solution, but here's one is trying to trigger the training. So what's the difference between these?
Yeah, the difference here is basically the continuous training is essentially saying that whenever anything changes, code, data, whatever, we are basically going to automatically train the system. A trigger training is what I'm just making up the word here, where I'm saying like you have a specific set of triggers, and you basically say I will only retrain if these triggering thresholds are met.
This evaluation,
Mhm.
but you can evaluate the trigger point. The drift is one of the trigger points.
Correct.
So
No, that in specifically drift is not one of my trigger points. My trigger point here would be time, right? Once a month, I'm going to train. That's a trigger. And the second trigger is I have twice as much data, so I'm going to train. Okay. Triggers other than drift. Okay, so maybe I should be much clearer. Triggers other than drift. The idea of drift detection is so hard and so error prone that you're often better off. Like in the real world, you're better off just forgetting about it and basically saying, I'm just going to do it once a month. Okay, and I'm going to live with slightly drifted models for up to 30 days.
Depends on the application.
Depends on the
Right, so if it is them running on the, for example, the cancer detection application, and I think it's okay, so maybe
absolutely.
based on some, running the same ML system, if I'm running in the forest, then 1 month is too long.
Yes, it totally depends on the application, right? So that's something we have to think about, and we have to basically say, is it once a month? Is it once a week? Is it daily? But the point is that you can avoid the complexity if you basically agree that we will just do it on a schedule, maybe a bit more often than these days compute time is cheap enough.
But for example, if nothing has happened,
Yes.
but if I am automated the schedule every day, it's waste of time.
No, okay. Again, these things are smart, right? So whenever you're basically, nothing has changed, the data timestamp hasn't changed and the code timestamp hasn't changed, you can basically just, it's like a make file, you can just immediately like drop it off. So does this mean that everything here is, that's not what I'm saying. Okay, that's not what I'm saying. There are situations that need complex. There are situations that need complex. So as an example, like I made the exact same argument about feature stores. That very small thing. Do you really need a feature store? And in most cases, there are unnecessary complexity, but there are a few instances where you do need a feature store. And the feature store you need if you're going to inject features server side, if the method of computing those features will be changed. If those two situations don't apply, a feature store is just unnecessary complexity. It's the same kind of subtle answer that we have to come to, right? We are not saying that you absolutely never need continuous evaluation. I'm saying that in the vast majority of cases where a 30-day drifted model is no big deal, don't spend all of your energy basically building a robust automated drift detection system because you don't need it. Just put it on a scheduled retraining and go on with your life. Okay? That's basically what I'm not saying that you absolutely don't need MLOps ever. I'm saying that in the vast majority of situations, you don't need MLOps.
If you design your system correctly.
If you keep it simple, right? So the idea here is you want to understand the situations where complexity is warranted, but what I'm saying here is that they are very, very, very rare. They're very, very, very rare. It's not that you need them in 80% of the ML models that we encounter in industry. You need them in less than 1% of ML models that we encounter. So this whole hype around you need ML ops is doing a lot of people a disservice because it's causing them to build unnecessary complexity into every system. 99% of systems have unnecessary complexity built into them if they buy into the MLOps. Okay. That's also because the simple solutions like Keras are becoming more powerful over time. Okay, so you can get away with it. The other argument is, fine, well, that's your own opinion, right? That maybe it's, all of this isn't just my opinion. Well, fortunately, when I do, now one of the advantages of my job is that I actually look at real world ML systems, both in Google Cloud and at Google. I look at a lot of real world ML systems. And fortunately, when I actually look at real world ML systems, they do tend to keep it. The ones that are successful, okay, the ones that basically are trying to, do this whole automation, they never actually make it out the door because they're sitting there in that the XKCD cartoon of basically trying to get their automation right, that they never actually get impactful ML models out there. It's much more important to have a working ML model than a fully automated. And so when you look at, for example, Pandera, right? This is basically, when we look at their data validation and their data preparation and their model training, it is all very standard data frameworks. They're not really using any ML frameworks. Okay? They're basically doing everything in Apache Beam and BigQuery and just doing SQL and happily going their own way because that is sufficient for automation. They're just putting all of these things on a schedule and they're getting their job done. And that's basically what I see in a lot of successful systems, right? This whole idea of like just keeping it simple is what I see in real life as well, okay? And another person that seems to have gotten this, and you got there earlier than I did, was I was looking for other, like, has anybody else talked about MLOps in this vein? And I saw that Todd Underwood had this talk on the truly hard problem in MLOps, which seems to be the installment MLOps. And when you go read his abstract, and he says the majority of the problems solved by MLOps solutions have their origins in clean ML data processing systems and are well addressed with the solutions that we devise to those systems. It's a weird way of saying what we say in paraphrase. The majority of problems that are solved, quote unquote, by MLOps solutions are already well addressed by modern data processing architectures. You don't need to build one more level of automation on top of it. If you're using a modern data stack, these things are already solved. Go on with your life. Okay? Is based. You don't need special ML processing architecture. So what do I mean? If you're using data warehouses like BigQuery or Snowflake or data lakes like GCS or Parquet files or Iceberg or Delta Lake, much of the problems that are being talked about as technical debt are already solved. So you don't need to build one more level of abstraction on top of it because you're doing ML, not data. ML is data. Okay, so you just basically piggyback back on top of all of the improvements in the data framework and also all of the improvements in the simplification of frameworks like PyTorch and Keras. And many of the ML technical debt things that were raised have been solved already. Okay, so bottom line, no, you don't need MLOps. It's not 2015. Modern data and ML frameworks provide simple solutions that provide simpler answers to many of the technical depth challenges that were raised. So you can avoid a lot of unnecessary complexity. You can keep it simple. Thank you.
Are there any questions? I guess most of them are students, so they may not even know what a technical debt is, right? Right. So,
okay. So what is a technical debt? This is something that's an engineering term. It's an engineering term that basically is around, like, if you have a software team that's building a product, they will often have a deadline to build a product. So we have to launch the product by December 15th. So now you basically you run into an issue. Okay, the issue is that you're building some piece of software. It will work as long as you have 30,000 users, but it doesn't scale beyond maybe 30, 40,000 users. You say, no, it'll take us too long if you have to solve this problem for more than 30,000-40,000 users, so we will basically file it. We'll take the debt, right? We'll assume that we will not have more than 30,000 users, and you build it. And then you launch the product. And then the next release comes along. You forget that you made this choice that you're never going to grow beyond 35,000 users. You build the next version of the product, you built on the first version of the product, you basically have all this leaky abstractions everywhere. And now you have your second layer. And the second layer also, you made a bunch of compromises. You build some more, and this debt keeps accumulating. And at some point, you have catastrophic failure. Okay? So that's basically what this is talking about. So when we talk about technical debt associated with machine learning systems, basically that's what we're saying. We're saying that by not keeping track of the kind of data processing that we've done, the validation that we've done, the assumptions that we've made, at some point, those assumptions are no longer valid because the environment changes. And by that time, the people who built the original system, they're all long gone, or they've forgotten about it, they're doing different things. And now you have this massive technical debt that your ML systems are operating. So that's basically what it's all about change, right? Life changes, therefore your ML models have to change in conjunction with them. But when you're developing things fast, you end up building debt. That's basically what it's.
Yeah, but it's such that also, right? You guys take shortcuts early on in the research pipeline, and then later, right? One day before you realize that.
We have a comment. Right?
Yes.
On the right-hand side point, but I would amend the conclusion as you don't need MLOps, specialized MLOps frameworks,
Okay.
but you would need MLOps as a concept, and it's solvable by general.
Absolutely. Yeah. So maybe I would say, no, you don't need what is sold as an MLOps.
So thanks a lot for attending.
So stop share and I'll stop the